Hi, I'm Kathleen. I'm a PhD student here at the University of Glasgow, and I'll be presenting Ichnos, which is a carbon footprint estimation tool for scientific workflows. So I'll quickly go over what scientific workflows are. Scientists have access to lots of cool new devices that can generate loads of data, and they've also got access to the internet, so they've got access to more data stored there. And they need to analyze that data to answer their research questions, to run experiments, or to run simulations. So scientific workflows are a method of automating that and making it so that they can rerun it depending on whatever new data they have access to. We've got a simple example shown on the right, which is just a basic pipeline where we start on the left on the first green task. Each task takes some data as input, does some random processing, and then produces output for the next task. And these have dependencies between them, so the later purple task can't run until the pink task has produced output for it to understand. So because there's so much more data for these workflows to process, they are typically long running, and that leads to a lot of energy being consumed and carbon emissions being generated from that. And we've got these scientific workflow management systems, which allow you to design workflows, to execute them and monitor them on distributed infrastructure. And there's a few different systems. We've got a few examples on the slide: Makeflow, Pegasus, and Nextflow. Nextflow is what the tool currently works with because I'm the most familiar with it. Yeah. So all of these tools can offer you the ability to generate performance traces, which can give you data on individual tasks, runtime, things like what nodes they ran on or how much memory was used, but it doesn't natively record the energy consumption or carbon emissions, which is the gap we're sort of trying to fill. So the specific problem, if you are a scientist and you want to understand the footprint of your workflow, you have two main options. One, if you care about it beforehand, you can monitor your energy consumption. You can use a physical parameter, literally just plug it in, or use a software parameter like RAPL if you're on an Intel-based device. But if you're working with cloud resources, then you might not have physical access to go and plug that in, or the machine type might not have tools like RAPL, or you might have to pay to use it. So there's not a consistent approach, and you have to set that up before you run it. And then after that, you're still going to need to estimate the carbon footprint, which is our sort of second option of afterwards. If we don't have that information, we can estimate it, and we can estimate the power consumption using resource utilization metrics that we get from these performance traces. And that's through using methodologies like green algorithms or cloud carbon footprint. I think cloud carbon footprint's been mentioned a little bit earlier. And both of these, when you use them, people tend to use coarse-grained average values rather than specific data from the time. So now I'm going to talk about the tool's design, and I've split it into three stages that I will go through now. So the first stage looks at taking input from the user. There's three items. The first one is a workflow trace. Nextflow handily enables you to get these traces pretty quickly just by enabling it in the config. And that generates a file that sort of looks like that, but a lot bigger, where you can get the number of CPUs, each task used, the utilization, the memory utilization, and the CPU model. It's just cut down so it fits as well, but there's loads more information there. The second item is the compute resource power model. These are a few examples of how you could estimate the energy consumption for a node based on utilization. We've got a linear power model and then one that minimizes experimental error, but the user's free to provide that. But if they don't have that expertise, they can always just use the default implementation of a linear power model, which is what we've provided. And then the third item of input is carbon intensity time series data, and you can get that from services like electricity maps, watt time, or in the UK, the National Grid API also offers that. But you can also provide a static average value, like the average carbon intensity from last year, depending on level of user. The idea is to sort of match carbon intensity data from when it actually ran. So the second stage is where Ichnos actually runs. So we've got the start where we take that trace file. I've just made it visual, but that's the sort of trace file that was text before, and gets the resource usage data we need from each task. So the runtime, the CPU utilization, and then we estimate the energy consumption using the power model that's provided. That's an example of a static or linear power model. So we measure the energy consumption at idle and 100%, and then estimate with that. And then we translate it into overall carbon emissions for each task using the carbon intensity time series data if it's available. And then we sum the overall energy consumption and the overall carbon emissions for our third stage, which is reporting. We will report the total energy consumption and carbon emissions in a trace file, well, in a sort of summary text file. So that workflow was an example, and it produced just under 5.5 kilos of carbon emissions just from one run, which is equivalent to around 31 kilometers traveled in a passenger car. And if you imagine that scientists will probably run their workflow multiple times, at least 3 ideally, so they're generating maybe like 15 kilos of carbon emissions just from one experiment. So in the extended abstract, we did 3 experiments. I'll just go through them quickly to sort of like illustrate the usefulness of the tool. So this is an example use of the tool with a workflow trace. So we've got a trace from a previous execution. We've got the carbon intensity value from, it's the average carbon intensity of the UK's grid energy last year, roughly. And we've got the minimum, the idle power consumption of the resources used and the maximum consumption. And then just running that in command line gets us the carbon emissions of 125 grams. It was just a small execution. And then we also produced a trace file that provides a breakdown of the carbon emissions, energy consumption per task. So we can then identify which tasks are contributing more to the overall footprint. See that some of them have 0.06 grams compared to other ones that take almost 6 grams. So you can dig deeper and then find out more information through that. And the advantage we wanted to highlight here was that it doesn't require you to rerun the workflow. You can use historical traces. So if someone's done research on running their own workflow, you don't need to rerun that again, and you can just estimate it. The second experiment looked at running a small workflow on a node that we had access to, and we changed the frequency of the processor. So we've got our results on the left. Then we also monitored the energy consumption using RAPL through perf, just a wrapper around it, sort of be like the actual value. And then we also had a baseline of using green algorithms to estimate the carbon or the energy consumption as well, using their calculator method as well. So both Ichnos and green algorithms overestimate this compared to the actual values, but Ichnos overestimates less than green algorithms, which we're saying is good. But in the implementation, we just used the linear power model. So we believe that by using a power model that was better at estimating for the actual resources used, we could get that overestimation reduced. And there's an inherent error when you're only estimating after the fact instead of monitoring. So you're not going to be 100% accurate, maybe. And our final experiment looked at the impact of using accurate carbon intensity data. So we could use the 2023 average carbon intensity for the UK, which was 215 grams of carbon emissions per kilowatt hour, compared to the actual carbon intensity reported by the National Grid for this region in Scotland, which ranged between 2 and 8 grams. And the green box is where the workflow, when the workflow actually ran. So we were able to estimate the footprint with both of these figures using our tool. And the estimate from Ichnos was 0.33 grams, whereas the one with the yearly average was 18 grams or something like that, but it's around 60 times larger. So we're saying that Ichnos allows you to improve your accuracy by using region and time-specific data when possible. So in terms of our future work, which we'll be looking at putting into the full paper, we've got 3 main focuses. One would be expanding our evaluation, so looking at testing the tool with more workflow traces on more resources, just to expand that evaluation. Didn't have much space. Our second area, we'll look at the accuracy of our power models. Ideally, we don't want to make the user have to provide a power model whenever they use the tool, because they might not have that knowledge or ability. So we want to look at automatically generating a power model for the resources through profiling. Yeah. Automatically generate that to reduce the load on users. And then the third sort of area we'll be looking at is using the tool to highlight the potential for carbon aware shifting, what the impact on the carbon footprint would be if we were to run a workflow later or in a different area, which some talks have touched on as well. So that's it. I've put a couple of links with the repository. If you want to look at it, it's open source, so anyone can contribute. The extended abstract and then my details. That's it.
Okay. Well, good job. Great job. Also, really good point on making notice that green algorithms and other frameworks overestimate, and it's really important to do power consumption in a really accurate way. I have a question about have you considered for your job like for example, when you're doing scientific tasks, sometimes you have like systems like Snorm where you put them in a queue and you wait. I see the potential to track carbon emissions in your work, but have you considered the fact that sometimes there are like queues, most of the research areas?
Yeah. It's, oh, I need to repeat the question. Yep. Now I need to remember the questions and repeat it.
You consider like the use of scientific workflows.
Yeah.
Because most of the time, like high performance computing areas have like queues. So.
Yeah. Okay, so the question was if we consider that when we're running on high performance computing, we might have queues where these jobs would get added to, and how we can maybe consider carbon emissions during runtime to then run it in a carbon aware manner. The answer is yes, that's the sort of like future research area. It's not something we're planning to do with this tool, but it's definitely something to address. The cool thing about Nextflow and other scientific workflow management systems is that they have ways of scheduling tasks. So we could look at trying to create a scheduler that we could consider the estimated carbon footprint and then look at how we could make changes or queue the jobs on different machines or at different times. But there's complexity there with scientific workflows having those data dependencies. We can't deal with all the tasks at once. We have to do it sort of on the go.
Plan to expand your scope and look at the networks and display devices. I'm assuming you're doing this right now with your own hardware, right? You're not sending it to the cloud. Looking at the display energy of your laptop or network if you're not over.
Yeah, so the question was right now, assuming that the experiments are running on local machines, but if we were to use clouds, would we consider the emissions associated with display devices or networking? Some of the future experiments would look at the costs and carbon emissions on running on cloud nodes. Network costs, we'll have to look at the overall footprint and see what sort of percentage impact that would actually have. I think we've had, I was reading some research that looked at how that cost would be negligible compared to the actual operational emissions, but it's definitely something to factor in, and it's not something we're currently looking at, but might do in the expanded evaluation, and definitely looking at cloud resources. In terms of display devices, not so much, because the workflows tasks tend to run in the back end and produce sort of files that then you can then look at afterwards. So it's a sort of separate cost rather than the cost of running the workflow.
Just if we have questions online.
I think we're okay here still. Yeah, no questions.
One last one. Yeah, so I like the work. Do you think that there's a danger when we quantify specific workloads that we lose sight of the bigger picture about the whole piece of work, where the punitive impact or the back-end facilities that are being provided just in case you're running? Amortizing the cost of the back-end or doing some stuff on punitive impact of the whole path of the work on this. See what I'm getting at?
Yeah.
Someone says to me, "Oh, well, that's only half the tree." I might go, "Oh, great! I'll run it 6 more times." Decreasing. Whereas maybe I'm really inefficient. I just always create models over and over again, and actually, Adrian is the problem, not the specific job.
So the question was looking at if by having all these like specialized tools for different workloads, if we lose sight of the bigger picture of where the problem actually is. I think it's an interesting problem. Like obviously by having more tools like this, we want to sort of increase the range of people that know about their own carbon footprint, and then it can be addressed. Somewhat away from the bigger picture because you won't be seeing the entire like data center costs, but that's also a different research area. This is sort of looking at scientific workflow specifically, and the scientists themselves might not know about their footprint, but by creating tools that they can use like this, then they can become more aware and maybe change how they use data centers, and then they can look at their own usage patterns and their own carbon emissions because there's only so much you can control from the scientist's point of view. They might be tied into using their own local clusters or have to use cloud resources.